Hey everyone, so today I'm going to talk about glyphosate for a bit and measurement of underivatized glyphosate and a couple of the other polar pesticides in mostly aqueous matrices using LC-MS. So for those of you who don't have a lot of background on this, glyphosate is a broad spectrum herbicide first patented in the 70s. It's been in the news a lot recently due to the fact that it is the active ingredient in Roundup. Roundup Ready crops themselves were introduced in the mid-1990s, and it's pretty ubiquitous in the environment in that it's widely used both in backyards and in agricultural fields as well. So glyphosate presents an interesting challenge for analysis, especially in LC-MS, because it's highly polar. It's a synthetic amino acid and a glycine analog as well. So here we have the structures of both glycine and glyphosate. There are also a couple other polar pesticides that are of interest to most agricultural chemists. These are amino acid synthesis inhibitors too, so glyphosate, glutamine. So these are metabolized by bacteria in plants, soil, and water into AMPA and MPPA, respectively. So here's a whole list, or really just a whole kind of image of the structures and names of different polar pesticides that are of use and of interest to chemists these days. So if you'll notice, most of these, or really all of these, have a phosphonate group, which makes them polar and difficult to analyze in LC for a couple reasons. One, their polarity, and two, phosphonate is a chelating agent, meaning that it likes to stick to any metals in your system, and all MSs and all LCs have metals in them, more or less. So there are a lot of other challenges, right? So there are various matrices this can exist in. You think drinking water is just one of them. It can exist in the plant matrices themselves. So if you're farming for fruit, it can exist in strawberries, it can exist in apples, anything kind of that you spray directly on or get spray drift from a nearby field. There are a lot of different regulatory limits around the world, and there are lots of different multiple extraction techniques between different places in the world versus different regulatory bodies, and so on and so forth. So there's liquid extraction, there's water extraction and cleanup on columns, there's QUPPE, which is a common one in the agricultural world. Basically, this is not an exhaustive list, it's just a common list of what's out there. Really though, what you don't see on here is just a simple dilute and shoot. There really isn't a good way to get this on a system, detect it in the environment, without a lot of work. And this is not even including derivatization. So most often in the past, this was derivatized in the lab and then analyzed, which means that that can take hours. It involves humans, involves human error possibilities. So basically you could do a couple samples a day. And for some labs that need to produce agricultural products, that sometimes just won't cut it very well because they can't run all their samples they need to run in a day. So the goal of this study was to kind of develop some sort of way to make this a high throughput analysis that was able to be done in an aqueous matrix. So if you'll notice here, a lot of these actually involve organic chemicals for extraction. There we go. So as I mentioned earlier, there's a lot of different extraction techniques. There's also a lot of different separation techniques. So these are all, think of them as like your columns in your LC. So these are all a list of different methods and what they call for, right? So there's Helix silica based, there's iHelix polymer based, there's simple reverse phase chromatography, which most LC-MS chemists prefer to stick to usually. There's ion exchange chromatography and ion pairing chromatography. So these are all kind of different. And quite different. Some of them more complex than others. Really what you want though is some sort of reverse phase chromatography usually. So the goal of this, right, was to kind of take the three interconnected pillars of liquid separation and mass spectrometry, basically, which are sample prep, chromatography, and then detection on your MS system, and kind of align them together to get a method that was both simple and sensitive. Right, so I mentioned we want to develop a simple and sensitive method not just for glyphosate, but for its other polar pesticides and metabolites that are of interest to agricultural scientists, as well as environmental chemists. Because if this is sprayed on a field, you can imagine that it's going to drift and also get into the water table. So for sample prep for drinking water, it's pretty simple. What we wanted to do was we wanted a method that didn't involve any derivatization, that didn't involve any type of exhaustive sample prep. So really all we need to do for drinking water was we filtered on a 0.2 micron PES, and then acidified with formic acid, basically. That means if we have 10 mils of water, we're going to put 0.1 mils of formic acid in it. Now, for the UHPLC conditions, we wanted something that was below 10 minutes runtime, something that could be high throughput, that we could run over 100 times a day. And we developed a new column for this work. So we have something called a charged surface column, which is different than your normal C18, and that it has sites that will actually help to retain very, very polar compounds. Mobile phases are pretty simple. Water with some formic acid, method with some formic acid. The injection volume is 25 microliters because we are in aqueous matrix here. We don't have to do a solvent exchange or extraction into organics. We can keep a high injection volume, which means that we can inject more sample if we need to, or less sample if we want to. That means we could get more sensitivity if we need to. Right, so key points here. This is these are typical LCMS mobile phases, right? And the aqueous mobile phase does allow a large injection if we want. So we're using Agilent hardware here. So we're using a 1290 HPLC and a 6470 triple quad of ours. So this is the detection and the chromatography pillars of that triangle. So these were the results of kind of our method. So we can see that we have baseline resolved peaks, sharp peaks for all of these very difficult to analyze polar pesticides, all really within 5 minutes. That extra 3 minutes to 8 minutes is really just column regeneration to get ready for the next run. So since this is going to focus mostly on glyphosate this talk, I figured we'd show mostly just the glyphosate data. So this is kind of our first pass of a calibration curve from 25 to 500 nanograms per liter of glyphosate. We have one with internal standards. This is just one that I'm showing without it. It's just cleaner this way. You can see it's very linear. We don't have really any, you can see there's actually quite a few replicate injections underneath each dot. You can kind of see them in the bottom graph, but we have really, really good kind of tight peak areas from run to run. We don't have any saturation occurring, which means that you could detect at very, very low levels, and then you could also detect high levels of glyphosate if you need to. So the top graph, or the top one, has 25 to 10,000 nanograms per liter. The bottom one is just a zoom in. So we wanted to calculate an MDL, which is a method detection limit. Think of it kind of like an LOQ, or a limit of quantitation. Basically, it's based on the reproducibility statistics for a series of replicate injections. So it's going to determine your on-column concentration where one is 99% sure a sample is unambiguously and reproducibly distinguished from baseline noise. So this was derived from the US EPA Clean Water Act analytical methods. So a lot of you may be familiar with MDL. So here we have an image of 10 replicate injections of 10 nanograms per liter glyphosate. So that's 10 parts per trillion, if you like to think in parts per. So here we have all the calculations. Basically, we did this on 4 different columns, 4 different column batches, really. We did 10 replicates. Really, the minimum is 6, recommended is 8. We wanted to go above and beyond, so we did 10. And we can see that we have an MDL of around, 6 to 8.6, 6.1 to 8.6 on all the different columns, which means we basically have an average MDL of around kind of 7.5, I'd say. And one of them was 7.5. That means that our detection limit on this method is 7.5 parts per trillion, or nanograms per liter, which is the lowest detection limit of glyphosate right now that I'm aware of. So basically, a summary is that we were able to develop a solution for the analysis of underivatized glyphosate and 7 other polar pesticides in aqueous matrices. So this presentation really only focused on 8 polar pesticides, but we could actually do some of the newer recommended ones, such as N-acetylglyphosate, which is actually quite difficult to analyze, but this method can hit it as well. We have well-aligned sample prep, chromatography, and mass spectrometry. So that means our sample prep is simple. It's basically a dilute and shoot, a little bit of filtering if you have solids in your drinking water. Simple chromatography, everything elutes in about 5.2 minutes. And then we have about 3 minutes of column regen. So total method is 8 minutes long. And mass spectrometry is simple, right? So we were able to see very good sensitivity on this method. And also very good dynamic range, right? Just because we were able to detect to 7.5 parts per trillion, we can detect also 10,000 parts per trillion with no issue. So, larger summary, it's very quick and simple. Sample prep, acidification is identical to the mobile phase system, so we don't have to worry about anything from our injecting a different solvent phase into our mobile phases. We have the column we developed for this. It uses a novel reverse phase packing. It's resistant to large injection volumes of aqueous head shafts. As I mentioned, it offers good retention of these polar compounds in acidic conditions and doesn't sacrifice the peak shape. We saw in our 6470, we have great sensitivity. The reproducibility and linearity is great as well. And the Mass Hunter software is compatible with dual polarity transitions for a given analyte. So I didn't show it, the transitions here, but some of them are actually in positive and some of them are negative, sometimes for the same compound, just to show that we can do that and still be quite sensitive, as some of the quantifier versus qualifiers are more sensitive in positive versus negative. So a couple additional resources here just to show, since you'll have this PDF or the recording. Kind of, if you're interested in this, we have a product page, we have a flyer. We actually do have an app note that I just published on this, or a technical note, whatever you like to call those. And we have a whole environmental solutions webpage too, if you're interested in our other solutions. And a couple of acknowledgements to some of my colleagues that helped out here. And I'll take any questions if I have a little bit of time now.
Yes, we have time for questions.
And we have some. Would this method work with a 1200 HPLC 6430 QQQ?
I haven't tested on the 1200 model. One of the things I would be worried about is back pressure. I forget what the back pressure limit of that system is. The 6430 shouldn't really have an issue. I just sometimes worry about the older model LC back pressures. But if you want to shoot me an email, so I think you can find my email, or I will type it in the comments and we could take this offline and I could figure that out for you. I also see some other questions. I could just kind of go down and answer them.
Sure.
So it looks like, is this method published somewhere? Yeah, so we just have a tech note that I published probably a month or two ago, maybe before that. But yeah, if you Google this, you should find it. And then, yes, so did you explore more complex water samples like surface waters? Yes. So we did do surface waters as well. We had to get the same detection limits, actually. This method I developed specifically actually for agricultural, the agricultural realm. I actually developed it for red wine. So this method is quite robust. I haven't run into a matrix where it falls apart. So this was kind of developed for a red wine matrix. And honestly, I haven't seen a matrix that's worse than that. Cannabis kind of gets close. So this works in kind of cannabis, red wine, black tea, as well as other complex water samples.